So now let's look at non-parallel forces. Non-parallel forces. So we have been looking at parallel forces, but now we are interested in looking at non-parallel forces. And when we are looking at non-parallel forces, we shall begin with the two forces acting on a body. We shall look at the resultant of two forces acting on a body. So if we are looking at non-parallel forces and we are beginning with the two forces, they are not parallel to each other, but they can be, if they are not parallel, that means that they are concurrent at some point, or they are meeting at some point, isn't it? Non-parallel forces, what we are calling concurrent forces. So we are beginning to analyze we are beginning with the analyzing two forces acting on a body. So we can say, if forces act on a body and the body is said to be in equilibrium, and the body is said not, if forces act on the body and the body is said not to be in equilibrium, then the resultant can be obtained using number of ways. Isn't it? So we are saying that in a scenario where we have forces acting on a body, but those forces, their effect is not bringing equilibrium. You know what we are meaning by equilibrium? Eh? Their effect is not bringing equilibrium. And then that force that is going to cause movement can be obtained using number of ways. How to get resultant of forces, that is what we are actually meaning here, that if a force has a resultant, then there are a number of ways you can get the resultant of the forces. One is what we are calling the parallelogram law. We can also use parallelogram law to get the resultant of two forces. Before we go to other methods like resolution of the forces, isn't it? That is for two forces. We can either use parallelogram or resolution of forces. And resolution of forces works for any number of forces acting on a body. But parallelogram only handles the part of only two forces acting on a body, and the forces must be non-parallel or concurrent or meeting at a point. So if that is very true, then our idea here can take us to parallelogram law. But then we can say, consider forces F1 and F2 acting on a body with an angle of theta between them as shown. That if we consider forces F1 and F2 acting on a body with an angle of theta between them as shown below, this is F1, this is F2, okay, as shown below. So, if this is the illustration, how do we now continue from here? We are saying that by completing a parallelogram from the forces, okay, we are going to transform these forces into parallelogram and extending the side AC to E and dropping a perpendicular from D to meet E extended. Then our drawing should be that if we complete a parallelogram from the forces, how do we complete the parallelogram? We do what we are calling transformation of forces. Transformation of forces, that is something to deal with, that if I have this force here, as F1, okay, I can transform it here. If it is at an angle theta, I can draw the same force here as F1, and if I call that theta, I've transformed this force. Is that okay? That it was initially here, but now it is here. And by the fact that a force is defined by the magnitude and direction. So if at all this force here was called F1 in a direction theta, and then still I'm calling it F1 direction theta, I've not changed the force, but I've just changed the position, but I've left whichever thing that describes the force the same, the magnitude and the direction. So that means this is the same as that, but in different points. And I can do the same thing to this one, which was F2 horizontally. I can also as well draw it here as the F2 horizontally. This is the same as that because I've maintained the direction and magnitude. Here it was F2, here I'm still calling it also F2. And we said this side here can be now my A, okay? Extending the side AC, this is C, and then to point E, they are calling it E here. This will be extended now. I can dot it, okay? And now this one is B and then D. Isn't it? So they're saying that computing parallelogram from the forces and extending the side AC should be extended to E. Isn't it? And dropping a perpendicular from D to meet at E extended. Isn't it? If I drop a perpendicular at E here, like that is a perpendicular. That is what I'm now talking about. And now remember, our interest here was all about getting the resultant of these two forces, which is supposed to be here as the R. Isn't it? So it is a matter of saying that our interest is here, getting this resultant R at maybe say some angle of alpha. theta is the angle from here up to here, but alpha is from here up to there. So that is now our drawing that we are going to use. And now if you follow us properly here, you will realize that here I have F1 sine over theta. And then here I have F1 cos over theta. That is what I'm basically having in there. So if I now say applying it, I can say from my triangle DAE, from my triangle DAE, if I apply Pythagoras, I'm going to say that if I apply Pythagoras here, I'm going to say, if I apply Pythagoras here, I'm going to say that AD squared is right angle triangle ADAE. If I apply Pythagoras, I say AD squared should be equaling to AE squared plus ED. Let me hope I'm not alone. We are together with you people. So, if this is very to applying Pythagoras on this triangle here, I'll say, but what is my AD? My AD is R squared is equaling to AE. What is my AE? AE is the same as the AC plus CE. Is the same as the AC plus CE now squared. From here up there is the same as add this plus that and then plus ED squared. And that means my R squared is equaling to AC is F2 plus CE is F1 cos theta. Okay? And now I combine squared plus ED is F1 sine theta, but also squared. Let me hope you're getting how I brought this. Because if I have this triangle here, if I have this triangle, we can say cos of theta is adjacent CE over hypotenuse F1. So that means that CE is F1 cos over. So from C up to E is the same as F1 cos theta. And then also if you look at sine theta is opposite, isn't it? Which is ED. Opposite of this over hypotenuse is the force F1. So you realize ED is F1 sine over. That means ED here is F1 sine of that. That's how I got that. So don't ask yourself how comes and how goes. This is still the idea of getting the component of a given force. So if we have now looked at that, I can now interestingly tell you that I have R squared, okay? I can now open bracket and say F2 squared plus, okay, 2F1 F2, okay, cos of theta. You know how to open that from your mass 1, A plus B squared. You square that one. Next time you multiply the 3 plus 2AB. Lastly, you square the last term alone. So go and remind yourself for now. We expand that from your pure mathematics. So that's what I did. I squared this and then I multiplied this times that, and then I'm going now to square this one here to give me F1 squared and then cos squared theta. And then plus this one also will give me, this is going to give me F1 squared sine squared theta. Okay? And then I can say this is R squared equaling to F2 squared plus 2 F1 F2 cos of theta plus, here I can remove f1 outside, f1 squared. I'll remain with the cos squared theta plus sine squared theta. Guess what? Guess what? Cos squared theta plus sine squared theta. Guess what? Run to your trigonometry very fast and Google this. Your pure mathematics, Google it from your brain. What does that one tell us? Cos squared theta plus sine squared theta equaling to 1. So that means that I will say my r squared equaling to f4 that squared plus 2 f1 f2 cos theta plus now f1 squared. Okay? Very, very, very important. So, if I proceed with my idea there, I'm going to drop to something none other than saying that my r squared, if I rearrange, is equal to f1 squared plus f2 squared plus 2 f1 f2 cos over theta. And it is very correct that r is equaling to f1 squared plus f2 squared plus now 2 f1 f2 cos over theta, and then this one under root, isn't it? And exactly this is what we are calling the parallelogram law. This is what we are calling the parallelogram law. That if at all I have some two forces, specifically two forces, they are acting concurrently at a given point. They are not parallel. They are having a point in common. And they